in robotics reinforcement learning. I really loved his lecture notes on about under-actuated robotics. One time I was reading it back and forth and was even trying to teach from it. So it's really awesome to have Russ here today, talking to us about future problems from robotics. Russ?
Thank you very much. I think many of you heard, but I was just saying it's been an awesome week. My only regret is that it's been the first week of classes too, so I've been juggling, but I can't wait to go through and fill in all of the things I missed. And it's my pleasure, but also my my problem here to give the last talk of after everything has been said. So I hope I can at least contribute a unique perspective, if not say new words. But here we go. So I thought this would be a good, following Alex and Peter, that I would first of all talk a little bit about what is working well in robotics and what's not. Just a little, but then start talking about simulation. Peter talked a lot about simulation. What role does it play in the work we're doing in robotics? These ideas of policy search that do connect back to control, like what Sean was talking about, and some lessons from parameterizations from control that I think are core questions and challenges that deserve this group's attention, maybe even this semester. That would be amazing. And since we've been talking about stochastics all day, I thought I'd tell you a little bit about some of our newer experiments in the rare event regime. And throughout and at the end, I'll try to make sure that I give at least a few of my sort of recommendations of like little nugget problems that are, are sort of pedagogically valuable, I think, for if you want to study these things in a robotics context. But to differentiate myself from the other talks, I figured I'd start with a robot that does a backflip. So, this is one of the things that control is doing very well, right? So, I cannot do some of the things that this robot is doing, and it's doing it with, our best ideas from modern control. It's solving, optimization problems in the loop, and it's doing backflips. Like, that's amazing, and that's so good. And even better in slow motion, yeah. And this is a model-based, optimization-based control approach. But keep in mind that this is, that model-based does not mean you're somehow wed to a super accurate model. We have no model of Andres in the back of the truck jumping up and down, right? That is just a disturbance, and the system is robust to it. And this was one of these late night videos from my cell phone. If the audio was on, you'd probably hear, sleep deprived giggling or something as we were doing that. This was right before the Big DARPA challenge. But this was an example of like control really doing everything it promised, right? It just worked incredibly well to stabilize a very complicated humanoid robot, 400-pound humanoid robot, solving optimization problems, robot doesn't fall down. But then there are things that, I can't do a backflip, but there are things that I can do, and I do all the time, that somehow all of our control tools seem to fall short, right? So the one I put in my abstract when they asked for it a while ago is, spreading peanut butter on toast. Like, that doesn't seem like that should be a hard control problem, but I don't know how to, we've got a lot of good algorithms, but I can't do this one. I can't make a robot spread peanut butter on toast. And if you watch, it's actually more nuanced than you think, right? There's a lot of very clever, force control. He's maybe reasoning a little bit about how thick the peanut butter is. He's certainly thinking about the edge. There's force control. There's pretty advanced perception. Okay, so it doesn't seem like that much of an ask to say, we'd like robots that are capable of some of the basic human skills, but we actually don't have it yet. So, that seems like an opportunity for RL, right? Because if the task is difficult, we don't have maybe the task is difficult because we don't have a model, right? But I think that argument has to be made very carefully. If you look at the world of simulation today, from computer graphics, from game engines, from, this is just one of my favorite new examples of someone who's simulating baking, okay? Like, and you can score the bread at different ways at the top, and you get different, you get all the nuances of like baked bread coming out. You can bake cookies, you can, don't bet against simulation, right? I think to say we don't have a model for some of the complex tasks, I think you have to be very, very careful about the implications you're making when you say that. So I thought I would dig in a little bit first and just think about what does it mean to have a model, and should we be using them in RL, right? So what role can simulation play if your goal in life is to, spread peanut butter on, let's say have a robot spread peanut butter on toast, and maybe have a robot, button a shirt, or there's any number of sort of household tasks that we would like robots to be good at. It'd be extremely useful if they were good at them, but they're just out of scope right now. I think just one of the sweeping sort of trends as everybody jumped back into RL and robotics, it was very interesting to see like the first couple of years where people were throwing a lot of the standard RL algorithms, but there was a pretty striking shift back towards model-based RL in the community. I remember at the 2018 conference on robot learning where it was just very clear from the abstracts and the talks that everybody was kind of coming in saying, I was doing model free last year, but I realize now models are going to help a lot. Not to say that's the end of the story, but it's just an observation from my perspective, at least, of what we've seen over the last few years. And it's led to I don't want to say a crisis, but like there's kind of this a conversation that's happening often about what those models should look like, right? And we have deep learning now, and deep learning does amazing things. And often a talk or a meeting will not go by until somebody asks the question, should we be doing deep models or data-driven models versus physics-based models? This was the name of the panel, data-driven versus physics-based. I didn't actually like the panel name, and I'll make that distinction in a second, but it's a conversation that's happening, right? So, and what does that mean? So here's some experiments we've been doing recently in lab. It's a relatively simple robot. It's an industrial robotic arm with a simple gripper, but it's being asked to do tasks that are outside our comfort zone in terms of modeling, right? So picking up that floppy hat and asking it to put it accurately on the rack, not only is that maybe hard in a conventional sense to model in a simulator, but the perception of that in order to close a feedback loop in reality, it has been traditionally very, very hard for us. Flipping up a shoe doesn't seem like maybe the world's most important task, but it's an interesting way. We went on Amazon and bought like 100 different shoes, and trying to write a single controller that could be robust to the distribution of possible shoes has been actually a really good exercise. And plates in like diverse environments and trying to show feedback. So this is maybe just a kind of problem domain I want to talk about for a minute here. And like I said, there's a big part of this that is actually a perception problem. And so I won't dwell much about perception in the talk, but just to tell you one of the key ideas, because you'll see it a few times here, but we do use deep learning in the front end for perception almost always now. And what you're seeing in this video is our correspondence network. So there's just a mouse in the still frame here. Well, they're moved, highlighting some point on a still picture of the hat. And the network is now outputting it's a heat map saying, what does it think the most similar points on this very different view of the hat are? And so to find the correspondences of this visual scene to this visual scene is already a hard problem, but it's something we've gotten very good at training deep networks to do. And it becomes a very useful front end for our more geometric thinking about robotics. So for instance, here's an approach that's maybe solves some of the control problems. We can just forget about offline policy optimization. If we can train a deep network model, in this case, we try to track a handful of correspondences. We call them key points in this case, but self-supervised key points. If we can just build a neural network model to predict the next step, just like what Peter was talking about, a model that says key points in this location plus action and controls, we're putting in the actions, right? And then predicts the next key points. Then we can use that in an online planning process to try to roll out and make some decisions. But the problem is when your model is maybe trapped inside a deep network, although the prediction of the network has worked very well, and we can do it for the hats and we can do it for all these complicated things, the model predictive control is still rookie. It's most of the people that are using deep models, forward models for prediction are doing very simple strategies like basically, random search to, cross entropy method kind of things in order to do their model predictive control, and surprisingly weak algorithms for the planning. And I think that may be fundamental. So let's just be a little pedantic here. So just to contrast slightly from the previous uses of the term here. So when I'm talking about a model, I'm thinking about a stream of inputs, a stream of outputs. There's not necessarily a start and an end. We're observing it and we can model it with initial conditions if that's of use. And we have a lot of models that take a state space form where we have our state. This is what Peter was referring to, and we have our noise and disturbances that Peter was referring to. But we also have parameters that define that model, which might be the physical mass of something or the weights of a neural network. And maybe we have distributions over all of those things. N in this case is my time, right? And Y is my outputs. I guess I forgot to label that one. Okay, but those are not the only types of models. And I think part of the discussion and the confusion in the robotics space these days is about the difference maybe between state space models and the input-output models that I think many people in this community are also quite familiar with. But you need not explicitly define a state. Of course, for any finite history, you can call that your state vector, but there are really important classes of models that are explicit functions of the recent history of inputs and outputs, don't make any Markovian state assumptions, and autoregressive models are part of the story too. And I think there's a couple things that are happening in the physics-based versus deep representations that are happening, right? So most of our physics-based models, if you will, the ones based on Lagrangian mechanics, when you turn the crank on the Lagrangian, the thing you get out is a state space model, right? Also, if you're training up a recurrent neural network, then you tend to use a state space form. But oftentimes, when people are training, let's say, image plus action to image type networks, which is commonplace these days in robotics, they're learning what I would consider to be an autoregressive model. So when people say, the image is my state, and then they give a slight history of images, I think it's healthier to think of those as input-output types of models. And just, I think the connection, I think people might not like the explicit way I say this, but everybody would agree that a Q function is a form of a model too, right? That's just trying to predict only one output. And I do think there's lots of people in robotics that are using Q functions in practice on non-Markovian state representations and having good success. Okay, so I think this whole discussion about what are the right models for robotics, should they start with physics or should they start with, should they just be deep models, is really about the class of models, right? Where F and G describe the model class, theta describes the model instance. And when people ask, and they do, right, deep models versus physics-based models, that's really a question about the model class. Should we prefer writing F and G using physics, or should we use deep networks? And to me, at first blush, that is maybe not so different than just asking, about a representational question about my network. Should we be using ReLUs or tanh nonlinearities? Should we be using, LSTMs or transformer networks or whatever? It's just an architecture question. But I really dislike the when people say things like, it's a kind of a pet peeve, like, is it data-driven or physics-based? And it's like, hold on. Every physics, when we say physics-based, we're still going to use data, right? Don't say that we've somehow given up on learning or data or whatever, right? I think the best data scientists we've had maybe are the physicists, right? That have come up with very simple models fit to extreme. Think about the noisy data that they were getting back in the day, right? And somehow they were able to give us this incredibly rich class of parametric models that we can now fit to data. And we do. We do system identification on physics-based models every time we use them in robotics, right? So it's not about data versus physics. And I don't know, this is a little cheeky, but I feel like when I've been saying it with my students, and it helps me like somehow sleep at night. But what if Newton had deep learning, right? Then and the output was here's the weights of and the architecture of my deep network. I think we'd be in a pretty different place in the world, right? So I think there's huge value that must be appreciated about being able to fit a complex model to data that is predictive. But I still long for more and more parsimonious models. And there'll be a little bit of a call here in this talk of trying to keep finding those parsimonious, simple models that we can do better planning with in robotics. So, when I go and think about the Lagrangian or Newtonian or whatever perspective of a problem like this, then, suddenly if I'm thinking about the state space of the problem, then there's a natural answer, right? It's there. Every one of those pieces has a pose. It's represented in some 3D SE3. It's got a spatial velocity, but the number of states is changing every time this happens. So it's a hybrid system, and somehow writing the state estimator doesn't seem like a good task, right? How do I estimate the pose of the piece of the onion that's somehow in the middle of the pile there? And so when you start thinking about these questions about what are the right models for robotics, I think the physics-based models are falling down, not because they're not accurate, not because they can't describe the data or even hard to calibrate to the data. There's other reasons about observability and the like. So what makes a model useful? And I think there's different use cases, and we're seeing that in a big way in the reinforcement learning world, right? So simulation is kind of one use case, and the Monte Carlo policy evaluation and the off policy optimization, that's a use case where I think having expensive, potentially hard to reason about models, but that can act like a black box can be very useful as long as they are predictive in the sense that things you get out of your simulator are resemble the things you get out of the real world. You'd really like them to also have some notion of coverage, right? Somehow the things that happen in the real world also can be come out of your simulator. You'd love it, although it's not clear if we need it, right? Because of importance sampling and other things, right? But you would love to have somehow the distribution of simulations match the distribution you get in the real world. And there is some sense, of course, where all that requires reliable system identification, which arguably we've been doing better at with deep models than some of our physics models, but there's incredibly strong results, of course, in some of the model-based system ID. And there's a bunch of other things that you might make a model better or worse, whether it's generalizable, efficient, repeatable, interpretable. But I think this online decision-making and the regret and the online optimization, these kind of questions, I think they really do force a different class of models, right? So of course you'd like them to be reasonable and accurate and generalizable, but somehow I think efficiency starts coming in a much more dramatic way. If I can't do planning on it with any reasonable algorithm, then it's not as useful to me. And if I have a state space model that is not observable, then it's very, very hard to use in reality. And then, a lot of times our models are trained on too much, right? If I'm trying to button my shirt and somehow the step one is to estimate the entire state of my shirt, then that somehow feels like I've estimated more than I needed to and maybe wasted time, resources, or even accuracy on it. And I think part of the confusion about how well deep networks are working compared to, physics models are working, it actually more comes down to the observability question, right? State space models, they tend to be more efficient and compact, but they require state estimation. And the prospect of state estimation, like I said, when you're chopping onions, does not make me optimistic, right? And again, the Lagrangian state is not necessarily the task relevant state. And I think maybe the bigger thing that's happening in the neural network world is really that we're building IO models, and that relieves us of the problems of state estimation, but it does potentially compromise some of our algorithms. By the way, I think that if we wanted to go to more IO models, that doesn't mean we have to throw away mechanics. That's an interesting path forward, I think. And just to finish this sort of point about the models, right? I think there is at least maybe one way where the physics-based models are sort of somehow fundamentally different than deep models or any universal approximators. And that's about taking a stand on what won't happen. I mean, physics models are sort of not universal, and that's great because somebody went out and took a stand and said, there are constraints. There are some things that will never happen, right? There's conservation of mass, there's conservation of energy, there's maximum dissipation, there's all these important rules that are constraints. And arguably, these constraints give our models their structure, right? And it's possible, I think, because the RL problem is so general, it has been harder to see the same kind of structured optimization results that we see on more structured models. In my manipulator equations, I can exploit the positive definiteness of the mass matrix and the branch-induced sparsity and all these different things, and we know it's control affine. And I wonder if there's a fundamental tension there about universal approximation and not having, maybe without any structure, we won't ever be able to do anything more than SGD. Okay, so that's a quick rant about models, but I think the failings of our physics-based models are actually more due to the unreasonable burden of estimating what I'll call the Lagrangian state and parameters. It's not that physics is wrong, it's that it's often coming in too detailed. And we are able to fit deep models for a lot of these problems that I've been thinking about and caring about laundry and food and the like. But they still fail me because I can't plan or do control design even offline with them very reliably. I'm missing my strongest algorithms. So I want the next Newton to come around and have him or her work on onions, laundry, and peanut butter, I guess. Okay, so here's another question or challenge that I would love this community to work on. Which I think is already on people's mind, but why, when, what rates does gradient-based policy search work? And just to add a little bit to that conversation from the robotics perspective here, right? People are using policy gradient and sometimes getting surprising results, right? Like, there was a lot of compute behind this, but even with all that compute, I wouldn't have a priori said, yes, it's going to find a good policy, right? And I think that's a very, very interesting and important question about understanding the cases when policy search is going to find a good policy, a gradient-based policy search is going to find a good policy, and when it will not, right? And there's a great community I think most of you, well, many of you might have known, but about this L4DC community, this Learning for Dynamics and Control is a new conference that is bringing together some of the controls community with the learning community. And I'm super excited about the prospect of these groups getting together. Some of the types of results that are getting discussed in that world are great. They're talking about convergence of policy gradient methods on well understood traditional control problems like the linear quadratic regulator. So it was very interesting to basically hear a result from Miriam, who says you can actually do the naive thing, which is just to search over the feedback gains, we call them K always in LQR, directly with policy gradient. We knew before she gave her talk that the objective was not convex in that constraint, but she showed that it would still find a global optima. And Mahaila's been doing more really nice work, giving some bounds on how quickly you can find those. This is a great trend. I think if we can grow the sort of sample complexity, understanding into more and more of these control problems, I think it's really good. But one of the things that was really interesting as these results started coming out, there were some people that were like, "That's amazing! I didn't expect that." And there were a few of the control theorists who were like, yeah, of course, right? And I've been trying to, get those people to articulate in a rigorous way this understanding that they had and why it was somehow obvious to them, if not for the rest of us. I guess I went out of order in my slides. And it comes down to the fact that there are convex parameterizations through a change of coordinates for these problems. I'll say something in a slide or two. And just even the existence of those convex parameterizations, which are sort of a smooth transformation away, there's a topological argument which says basically if there's a convex parameterization that lives over here, then there should be you can't lose you can't introduce new local minima through that transformation. So if I make any contribution to that, it'll be getting those folks to write it down carefully. But I think it's a super exciting trend. But there's also reason to think that stuff shouldn't work. Like you shouldn't just be able to to search over feedback gains and expect global optimization to work, global results. And so here's the simplest example that I like. So this is now, instead of state feedback, the reason it's not a counterexample of the previous problem, the LQR result is about if you had U equals negative KX, okay? But it's different if you have U equals negative KY and you have an output system here. So now you're doing output feedback, and this is static output feedback, okay? And this is a particular one where you've got your feedback parameterized by a scalar K. And the reason I say it's a claim it's a counterexample is because the set of stabilizing K is actually a disconnected set, right? So I can give you 1K. In fact, I wrote a couple down here. I can give you 1K, 0.9 if you started there. There's another K in between there and where you want to be that is unstable, just flat out, unstable. So independent of the objective, basically, essentially independent of the objective, this is not going to be good for gradient descent. So it's super interesting to think about, is somehow the OpenAI hand or DOTA 2 or all of these examples, how is there some reason why that they actually worked, okay? So what characterizes the good cases, right? So maybe it's the overparameterization of the deep policies, right? But and I would not be surprised if there's some comparable story to the interpolating solutions in high dimensional policy space now, that we're understanding better for supervised learning. But I don't have it yet, and maybe someone here does, but I don't have that yet. I don't understand how deep overparameterization is enough to give me convergence to a good policy. But maybe it could be other things, right? So I think control has traditionally studied algorithms, even when it's not about worst case results. Somehow there's just even inherent in the problem statement is this idea that this controller must work for all possible A, B, and C, even if there's no robust control analysis, even in the nominal case. And that's very hard. Maybe the world never, that can mean systems, linear systems that have poles and zeros interleaved in some evil way, right? And maybe those just don't happen in the real world. And maybe if we're doing, more targeted policy search on distributions of problems that are generated from physics simulators, maybe something how better, or maybe even adding of course, adding stochasticity can potentially smooth out the landscape, but maybe it's actually making the landscape fundamentally better. So I don't know, is it the distribution of tasks? Is it the overparameterization? Is it both? But I'd really like to know, I'd like to have confidence if I had a new problem, do I think policy search is going to work for that? Gradient-based policy search is going to work for this or not? I think there are other important lessons from control. For instance, from better controller parameterizations. And I started talking about this a little bit. So, just because you can search over U equals negative KX and find the best K, it doesn't mean you should, right? So if you start doing these convergence analysis, then you're going to, I think, be unhappy with the rate of convergence, right? And it also is related to this idea that the set of stabilizing K is non-trivial. You have to be potentially careful to not walk out into an unstable model. Okay, just as a simple example, if you do have a model, then it could be better if in an LQR problem where your cost is parameterized by matrices Q and R, why not search over Q and R? Because then for every positive, now the constraints are trivial. For every positive Q and positive semi-definite Q and positive definite R, I get a stabilizing K out. So maybe that's a better thing to search for. This is something we actually looked at a while ago. And it does bear out in simple experiments, that searching in Q and R is better, but there are other parameterizations that are well known in the controls literature that are even better still than that. So for instance, for LQG, H infinity, and some of these other linear type optimizations, we know convex parameterizations, like the Eula parameterization is another one we looked at in the paper, which is a form of disturbance-based feedback. And that, for the linear problems, actually convexifies the parameter space. So I think it should be a much better landscape, and it seemed experimentally to be so. Of course, we have, Eula's in the time domain is got some limits. There are LMI formulations of LQR, for instance, that use different, would suggest natural, reparameterizations of the problem that could potentially help learning rates significantly, right? The result of those ideas feels restricted to linear systems if your goal is to get convexity out. But my guess is that actually, if you just care about convergence rates, somehow regularizing the problem, getting rid of bad conditioning and the like, I think that those lessons are probably much more general. So here's the Eula parameters, just the simplest possible case of the Eula parameters that I thought I could put up in case people haven't seen it. So this is my standard LQR problem at the top. Okay, normally this is an over, in finite time problems, we can express the feedback law as a time varying function k of n. Okay, so in general, I might have to search over a different k for a different x. If I have a finite, that's just like your finite dynamic programming, right? But if you think about and this is the standard way we write down our k, our feedback law. But the problem with that is, of course, that if you start taking it through the dynamics, then you get k's multiplied by k's, get the multiplied by k's, you get some non-convex combination of k's. So your decision variables are highly non-convex. Your objective is highly non-convex in your decision variables. So the Eula parameters, in the case where there's no noise, is actually trivial. You just say, I can express exactly the same policies by just parameterizing everything off of x0. Okay, that sounds a little silly, but I'm going to say u at time 4 is still just multiplied by x0. If there's no noise, I can just roll my model forward. I know what xn would have been. And that gives me now only an additive, a linear dependence on the parameters in my rollouts. Okay. And then if you do have disturbances, then you do disturbance-based feedback. So you still parameterize u as a function of only x0, but then you can additionally add in coefficients times the noise, which you can actually infer back in a causal way. Okay, and so this is just a way for finite time problems, or in the frequency domain, it's mostly presented in the frequency domain. It's a way to make your problem convex, and this should be a better parameterization, even if you're doing stochastic gradient descent. And that's maybe what the linear control tells us, but I also think there's lessons to be had from the roboticists, and like the domain experts. I call them the robot whisperers. I was talking to Stephen Boyd the other day, and he says, "Oh, you mean Bob?" Every field has like a Bob, which is like the domain experts that always have the right answer, and maybe can't explain why it's the right answer, but there's always somebody in the back room that sort of completely understands the problem, right? And I know a bunch of them, right? This is Andy, is actually the person in this video from Boston Dynamics who wrote the controller that makes the robot open the door, and it's like super ridiculously robust, right? And there's no learning there. That's a hand-engineered controller that Andy had enough domain knowledge to think through all the possible things that somebody could do to make that robot, struggle to open the door. And the door almost always gets opened and the robot always gets through, even when he starts abusing it. Okay. And it actually, there's a longer history too. And this is one of the ones I would say is a good canonical problem for people if they're interested in like a toy robotics problem. So this is actually, this is the 2D hopper. I know there's a hopper in OpenAI Gym that's with a foot on the ground. This is the real, I guess, hopper from the MIT Leg Lab in the 80s. It's a beautiful example, and it actually evolved into all the quadrupeds and the like that you see from Boston Dynamics today. But the thing that was amazing about it was the intuition and the simplicity of the controller, right? So this was at a time when the robots were moving very slowly. This robot started throwing itself through the air. But the amazing thing is that the control description, like the book, there's a nice 200-page book or whatever, but the controller description fit on a single page. I mean, this was the diagram at the top of the page, and there were a couple like PD controllers right below it on the page. And that's not unique to this. This is the way people write controllers for practical robotics. They tend to have little state machines. They're guarded on some, simple events. Reach down until you touch, pull until you feel this. If you feel something crazy, transition. And you know, it's always annoyed me that despite all the optimization, you give me a perfect model. I don't know how to write an objective or solve an optimization problem that would give me a controller that is better than, that is in some sense more robust than the one that was written on a single page. There's so much baked in intuition about what works on real robots that it's very hard to beat. And I think it's a standing challenge for us in, let's say, optimization-based control. Okay, so since I knew we were talking about rare events today, you know, I'm not an expert in it, but I've been thinking about it more and more because I think the problem domain needs that type of thinking. And so I thought I would you know, show you some of our experiments with it, and me getting my head around it. Work with some really good students who are experts in it. But let me tell you that in the form of a story, right? So we're getting to the point where for some tasks, robots actually fail rarely. And the learning that we want to do is really in the corner cases. So here's an example that we've been working on at Toyota Research. It's about loading the dishwasher. So that's Siwan. He is one of our robot whisperers, by the way. You know, he dumps stuff in the sink, and then we let the robot go. And actually, the robot goes kind of all day long. Well, pre-COVID, it went all day long, every day. You know, and its job is to load the dishwasher. And you know, it throws the refuse in the pile on the right, and it puts the mugs in the top shelf. It puts the plates in the bottom shelf. It puts the silverware in the silverware rack at the top. And it's really complex, but it's really pretty robust. It fails, the whole task fails very rarely, even though some individual components will fail. It's got layers of robustness that make it, you know, get the task done almost always. And it's really taken us to this point of trying to understand how to make a system like that. It's still not good enough. It fails regularly enough that you don't want it in your kitchen, right? But it's empirically very hard to find the corner cases which cause a good policy to be differentiated from a not quite good enough policy, right? So we do have simulation for this. We've made a huge investment in simulation, and we simulate the thing all the time, and we can run lots more simulations than we can possibly run hardware experiments, but still it's not enough, partly because we don't know the right distribution of simulations to run, and we lack some of the really fundamental tools of trying to take rare events in reality and bring them back into simulation. You know, those are the hard parts, is calibrating distributions of simulations when the lighting conditions matter, the shape of the mug matters, the friction properties matter. You know, those inverse graphics problems are pretty tough. But we really are in this regime of subtle bugs. Like we finally, after watching the robot for a while, we saw it start failing very rarely, but in this funny way where the robot would pick up a mug, start going to put it down, and then like decide it couldn't set it down, so it would set the mug back down on the counter, and it got in like this infinite loop. And it turned out that the reason was that there was some perceptual noise in the estimator of where our dish rack was, and there was a like diabolical position that the dish rack could get itself in, where with very high probability, the robot, when it was picking up the mug, said, yeah, the dish rack is open, started moving. But with very high probability, before it finished setting down the mug, there was at least one sample which said, nope, that dish rack is too far in. And we had, you know, too fragile of a threshold in the middle of our huge complicated algorithm. And so the robot would, you know, set the mug back down and then just get in this infinite loop. And that was very, very hard to find, but we found it eventually in simulation. And then we saw it on reality weeks later. But so now we make simulations look like this, right? This is our importance sampling, right? This is like, the poor robot is tortured because the dish racks are just moving like crazy all the time in every simulation because we want to excite those corner cases. Okay, but this was a human-tuned importance sampling strategy, and how do we do better, right? I've been working with Matt O'Kelly and Aman Sina and John Ducci and a few others on trying to understand how you would do rare event simulation for that class of problems that has, you know, all the complexity of a deep neural network perception system and a complex physics model and everything. And you know, these guys have made some really exciting progress. So you know, there are a couple key ideas that I'll just communicate quickly, but one of them is changing from falsification to estimating the failure of probability. And they're using tools from adaptive multi-level splitting and Hamiltonian Monte Carlo and doing some neat new tricks with normalizing flows in order to do some parametric warping of the distributions, of our sampling distributions. And I'll show you sort of quickly what that looks like. So, one of the problems with our my traditional, let's say, formulation of just trying to find any counterexample, any failure case, is that you tend to find the same type of failure case over and over again, okay? And fundamentally, if we just say this is a failure, run your simulator, find failures, you tend to not get coverage in the way you'd want to. So if there's, a pretty non-convex landscape or whatever, there's really no incentive for my falsification algorithm to find different failure cases on each time. If we change our question from, what's the general form of the question where you would get some diversity, we've been pretty happy with this much harder problem of trying to estimate the failure probability, right? If I say, what's the probability of that function being less than 20, then in order to get that probability right, it has to somehow visit all of those states, right? And of course, it's a harder problem. So we've been working with the risk-based framework now, right, where we're trying to do importance sampling by, prioritizing the heavy part of the distribution that we care about in the failure region, and learning samplers in these, in these warping functions in normalizing flows in order to learn samplers that work in this regime. We'll pull from those regimes. And in the toy problems, they look, intuitively exactly what I'd like. I take a simple problem of sampling from the unit covariance, normal distribution, and having a rare event of just trying to get a sample that was greater than 6. And okay, and that's extremely low probability. And we get these these Monte Carlo approaches to build a ladder of samplers that will eventually sample very frequently in that domain and give us better estimates of the probability of failure with asymptotic bounds. I like that conversation. But the cool thing is they've been able to find super complicated failure cases in really full-on models. So the best example from Matt and Aman so far has been, in my opinion, is this, they put the full comma.ai open pilot, autopilot basically, into a full simulator, this Carla simulator, and started sampling over really diverse lighting conditions and other things. And let me just play that again. So what's happening here is they caught a failure case where, I kid you not, the sun gives a flare off the back of the windshield of the previous car, and it causes a crash, okay? And the cool thing is, if you look at the open pilot output, it actually knows that it's uncertain about the location of the previous car, but the controller did not change course and ended up still making a mistake. So, I'm excited about these algorithms, not just because they're finding some corner cases, but because I think more fundamentally, it feels like the right kind of spec that could scale to the complexity of problems we've been asking in robotics and autonomous driving these days, right? So super high dimensional black box models, empirical risk estimation. I was skeptical that we'd be able to make any progress there. I am excited about what I'm seeing so far. Right, so, and I really think, asking for a autonomous car that can never crash is probably not the right formulation. Asking for a robot that will never break a dish is probably not the right formulation. But what I think we should be aiming to do is these empirical risk estimations. And the connections to RL are just waiting to happen, I think, and let's see if they can play out. Okay, so I'll just end with a couple, specific problem instances that distill some of these kind of problems down to things that are, AI, OpenAI kind of benchmarks. I mentioned one, the hopping robot is a great example. I've considered it a standing challenge for a decade in under-actuated robotics, right? That none of our optimization algorithms can do as well as Mark Rabert's one-page controller. The dishwashing gave us a couple other really good benchmarks, okay? So there's a subtle controller written by a robot whisperer, C1, that picks up plates, even when there's stacks of plates and even when the sink is cluttered and everything like this. And it works really, really well. And we've been trying to replace it with a learned policy. And we haven't got a learned policy that will outperform C1's hand design controller yet. We're banging on it, and I actually think we might do it, but it's connected to this rare event kind of idea. Is, I mean, the many examples of picking up the dish are actually pretty easy, but every once in a while there's a really hard one. And somehow C1 had all these, all these things in his head when he wrote that controller, and he guarded against them beautifully, and I can't get the algorithms to do it yet. Andres has been working on this along with a few other super strong people at Toyota Research, and we've got it down to what I consider to be a textbook problem with very simple. We have even simpler models than this, with like point fingers and distributions over plates that I can write down as a POM-DP and actually solve. But then you start running into the limits of your model. This one is doing policy gradient on a fairly simple model. It's fun to watch all the standard outtakes you get when you're doing RL. The first thing we asked was just that the plate gets to a certain angle, and it managed to go and flip the plate up in the air, and all the good stuff. But this is one I'm actually putting into my new notes, my manipulation notes, as I think it deserves to be a sort of textbook example for multi-contact control. And we are hammering on this with not only all the different methods from policy search to POM-DPs and everything in between, but we're also trying to attack it with rich distributions over possible tasks. So distributions of plates, of mugs. We have procedural mug generators that have a small number of parameters that generate a diversity of mugs that capture what we see. We have parameterized lighting conditions, you name it. Okay, so there's also, I think we need something that's kind of a simple textbook example for the kind of problems that we saw OpenAI deal with. And we have one that I like now in this, we call it our planar gripper. Rick and Honkai have been working on this. Also, I think it's ready to be a textbook example. And there's a few other people that have things that sort of look like this. We actually have hardware that looks like this too. But this is kind of boiling it down to the plane, to its essentials. It's still a very rich multi-contact problem, but it's something that I think we can hammer on and really understand. And all of those are, so I have a new set of notes for manipulation now as of this fall. Well, they're being written, in real time. But one of the things that COVID did for me, well, I don't know if I would have done it anyways, but I spent my summer trying to make sure I could teach class remotely really well. And for those of you that did download slides.com, you're actually running a live 3D render of that. You can all twiddle it yourself. And I got it now so that our robot simulators, our high-end robot simulators, can run in anybody's browser with zero install. So in fact, after we're all done here, if anybody wants, I could get them running a robot in less than 5 minutes. So, okay, how well is control working in robotics today? We talked a little bit about it. Backflips, yes. Peanut butter, no, right? Okay, so I think simulation has a really important role to play, but it's still hard. And it's interesting to watch people struggling with physics-based versus deep models. I think there are some great questions in gradient-based policy search, great questions about the intersection of control and RL in the parameterization level. Super interesting things to do with the rare event regime. Overall, I'm just overwhelmingly excited that the theorists are coming and to help me with my problems, I hope. Please. So we have good challenging problem instances. I named a few of them. Onions and shoelaces, we have some canonical versions of those too. I didn't think they'd fit, but if you are interested in this kind of stuff, I am sincerely interested in bringing more theoretical understanding into these problems. So drop me a note. I'll end there, but I'll say that if you do actually want to run a robot right now with no install, then this is what you would do. You can actually in your browser right now, this is a live link, and anybody who used slides.com, you can just click on that button and click the first cell, and that will install the machine on Google Cloud for you, and I will talk you through it after any questions are done. If you didn't use slides.com, you can just go to that website, go to chapter 1 and click on Open and Collab. Okay, I'll stop and take any questions.
Very cool. Thank you. Yeah, very intriguing. So we do have one question that I was saving to the end. It's from Aaron Snowswell. Says, hi Drake, question about physics data models. Recently, the machine learning reading group at my university has covered a lot of papers on deep Koopman operator theory, learning good latent linear approximations for complex dynamics from data. Love to hear your thoughts on this sort of approach to the simulation problem.
Awesome. Yeah. So, I mean, Koopman operators are a cool idea. Everything's linear if you're high enough dimensional. And that's and it's connected to occupation measures and other things we know from control. The question is just how high dimensional do you have to get before things get meaningfully linear? And I think for contact type problems, it's pretty daunting. So I will completely admit, there's probably some 6 or 12 month cycle where I'm like, oh, we should try that again, but I'm not in one of those cycles right now.
I guess I've seen a talk from you just half a year ago when you were still in that cycle, or like you were coming out of it or something.
Maybe. Occupation measure, yeah, there's good stuff there, but it's
the onion cutting stuff. Yeah,
yes.
I remember occupation measures there showing up. Yeah, cool. Lots of good stuff here. So I have a foundational question. So do you think that so we in RL theory tend to think about the algorithmic problems, like how to design RL algorithms and like different classes of problems, not so much, right? So like we put on our machine learning hat and we try to be model agnostic, right? So we are kind of inheriting that from the whole field of machine learning. Is this?
You're also asking about sample complexity and the like, and right? And wouldn't you expect that there's classes of problems that you would get much, even if you have a generic algorithm? I'm okay with. I also have a slight preference for algorithms that are not too wed to any one problem, but wouldn't it be great if you could understand that those algorithms work super efficiently in some classes of problems, and especially if the real world dished up those problems often?
No, I actually wanted to ask you whether this is something, this is a mistake or not, or we should be, like, should you take a model first approach, think about the classes of systems that you need to control, and then think about what type of algorithms you should be using for this type of systems, rather than taking a wholly generic approach that, okay, it's great because it's general, it could be applicable to many things, but maybe overall it's going to be just too weak.
I think so. I think we're there. I mean, I think we're seeing that, right? I think the fact that we can write a policy gradient algorithm for any problem is cool, but it's not going to converge for every problem, right? There was a trivial counterexample in the talk, but so the fact that we're seeing people use it effectively and getting convergence means there's something deeper to understand about even the simple policy gradient algorithms, I think, right? Is that, there is some class of problems where people,
okay, so
go ahead.
You're flipping the question there. You're saying that, okay, you have this algorithm and it seems to work well. What is the class of problems for which this works well? Let's understand that, right?
You're right that the other side is super. In fact, I'm maybe more interested in the other side, which is that you should be able to make more powerful algorithms if you restrict the class of problems, right? And that's, I guess, what robotics has been doing more traditionally, right? So I've taken as my class of models the manipulator equations, right, that have certain structure, and we've written much stronger algorithms because we've restricted ourselves to that. It doesn't feel very restrictive, but it's a class that's much smaller than all x dot equals f of x, right? And I think you kind of need that in order to write stronger algorithms.
That's kind of funny that you're saying that, because on some previous slide you had this slide about the potential challenges that come from Lagrangian state, right? And all, like, every time we write these models, like, we are just so inherently strongly relying on that concept. And then if you have a perception action loop, then that state estimation problem maybe just killing everything, like all the advantage that could come from the model. I guess that's the tension, like, how do you, like, do both at the same time?
So I have a hope. I think we are, if you use the naive generalized coordinates from Lagrangian and write that, I have a class of models I can work with, but they're not useful in the state estimation sense. I have to believe that there are other models that are not arbitrary. There's another class of models we haven't found yet, that where somehow my single onion turns into a pile of onions, because I don't think about every onion anymore. There's something that happens, that somehow I'm starting to think about it as a pile, except for when that one little piece gets close to the edge of the cutting board and I have to pull it back, and suddenly I attend to that. And there's all these ideas are still there, but how do you write a class of models that is not arbitrary, is not universal? It has structure that's exploitable, but it works in this intuitive physics space. That's the question. I mean, I think very simple models can solve those problems. I just think we haven't spent enough time trying to find them.
Yeah, I see. So, like, the Eula parametrization or anything like that, where you have something in between the very strong model-based approach, which very strongly relies on the structure of the models, and, like, something that's a little bit less on the parametric side. I don't know.
So okay, the linear models seem not rich enough for pushing carrots around or onions around, right? But maybe piecewise affine models are, like, we know pretty well how to do that. They're hard to fit. They're combinatorially bad to fit optimally. But that's a class of models that I can write strong algorithms against, and I can think about approximate planning solutions and all these other things. Maybe that's good enough. Maybe that's still kind of too specific, because probably I only I don't need to have a detailed prediction of first, what's the state in that piecewise affine model? But if I could come up with, like, from the key points or something, one of these representations we've been playing with from perception, and fit, whether it's a low, I don't want it to be low dimensional. I think that's the wrong notion of simple, but something that I can efficiently reason about. So maybe it's a small number of pieces in a piecewise affine system, or maybe it's, there's some other metric of tractability. And what's that right model class? Right, F equals MA was a pretty good one
for a while,
for a lot of things. But and maybe it is still F equals MA, but not A being the generalized coordinates.
Yeah, I guess that completely misses out on the perception aspect, and that's the challenge, right?
But I think you can get intermediate representations out of perception that you could learn simple models on. I don't want my ResNet in the simple model. That's not simple, right? But maybe I can use a perception front end and predict, relevant strong features that come out of a perception system and how they move forward in time. And that's the kind of models we've been thinking about.
Okay, but you're definitely saying that if you want to make progress on these challenging instances, we should specialize the algorithms in some way. It's not going to fly if we just, like, stay at the level of, oh, actor critic, oh, policy gradients, oh, value-based method, deep Q learning, whatever, right?
I don't fault people who are studying that, but I'm likely to be the one. There's a lot of good people thinking about those. I'm going to try to think about the structured models. That's my personal preference.
Okay, interesting. That's your bet. Yeah, bet. Someone was saying that you should also name your stake if you're betting. Anyways, maybe we can play that out offline. Okay. Good.
if anybody wants to, if they've clicked far enough through in that simulation.
Oh, yeah, like I posted this in Discord, so people could try that.
It's a Jupyter notebook with 3 cells. If you ran the first one, it takes 2 minutes to provision the cloud machine. You run the second one, you will get a simulation of a robot arm that you can now drive around and try to move a red brick around. And that's just like,
I see that Aaron was actually already doing that. Cool. Yeah.
So I'm excited about, I think some of our most advanced robot simulators can be pretty accessible now. So I'm teaching that course online. If anybody wants to follow along, it's open, pretty open. So.
Yeah. All right. So one more question. Quick thoughts on the state of training, pre-training in simulation. How far are we from solving the challenges without extensive hand-tuning of the simulated environments? I was also thinking about this so-called sim to real question.
Yeah.
So what do you think?
Okay, so I think, again, there's lessons from robust control. So there's a notion of, I think, if you have lots of control authority, then your model can be very sloppy. And you can expect sim to real to work because you can just overpower the uncertainty and the like. You can ask it to be robust to anything. And to some extent, a lot of the sim to real work we've seen, the fact that people are putting like cheetah patterns and checkerboards and whatever all over, and they're training their perception systems against that, and they're changing friction properties between like 0 and 10. I mean, that's coefficients of friction of 0 shouldn't be good, right? But and somehow they're still getting something to work. That means the problems we're solving in a control sense are pretty easy, I think. When you start trying to do more complex tasks that are more at the limits of performance, then you're going to need to get tighter models in order to have those transfer, right? If you ask yourself to be robust, if you're like the Millennium Falcon trying to get, as the doors of the Death Star are closing, and then you got to have a pretty good model for that. Otherwise, robust control is going to say, no, I can't do that. I can't give you a certificate that for all possible Death Stars, it's always going to work. So the question is, where I think there's tons of interesting problems in robotics, in manipulation, for instance, where they're actually pretty easy and the simulators don't have to be that accurate. But it's also been interesting even like 2 years ago, my students would have said, you can't do manipulation research in simulation. It doesn't work well enough. The perception, the simulating a camera is too hard and simulating contact is too hard, too difficult, let's say. But that's changed in the last 2 years. And I'm very optimistic about how far it will go.
Interesting. Isn't there a challenge in figuring out what parameters of the simulator to change and what to shake, what to rattle, to what extent? And like eventually I have the feeling that if you try everything, there is another combinatorial explosion that you're facing. So maybe you should be a little bit more smart about how you're doing this.
Yeah. There's also, for the, the general RL theory community, I think that there's interesting questions about how accurate your distributions over parameters need to be, right? Do we need to have the probability of a simulation to being right, or do you just need to have coverage, right? Because maybe you actually, in an important sampling sense, you actually want to have the rare events happen more often, right? So am I just fitting uniform distributions to every parameter and that's good enough, or do I have to tune in something with really high fidelity? I think we don't know what the demands are from the synthesis algorithms yet. But and you're starting to see people in robotics, at least. I'm sure other domains are doing it too, trying to fit, probabilistic models to more and more complicated situations where you're trying to get not only just somehow some maximum likelihood estimate out, but you're trying to fit the distributions. We're trying to get distributions over our certainty of the mugs and have probability fly all the way through the system. So yeah, we'll see. It's not easy. Lots of data. So that's the one thing, is I think robotics is about to be, the type of robotics I'm talking about, of home robots and the like. It feels like we're finally going to get to be one of those fields that has big data. It's getting close.
Because you have,
and we're going to have more robots, right?
A different question. So in reinforcement learning, we traditionally formulate reinforcement learning as a single objective optimization problem. A recent pet peeve of mine is to get people's opinion about like how limiting is that.
Yeah,
I think that we should stick to the single reward objective, or should we expand? How important is that?
If I had to place my chips, whatever, I give you a stakes or whatever, I think that trying to solve every problem is too hard. Trying to solve a single problem, single objective is too narrow. I would put my chips on trying to solve a distribution of tasks, a distribution of problems, right? If you get one control parameterization that can solve some family of problems, then maybe you get some of the benefits of being problem specific, and even possibly some of the benefits that would come from not being too problem specific. But I mean, certainly
I guess I was not super clear. I was more thinking about, like you'd have multi-objective optimization instead of a single reward function. I don't know whether that was clear.
I see.
But like in a robot, like how do you, like, what's your reward function? When you want to, you mentioned that when you first ran the experiment, the plate was just flipping in the air. You didn't like that solution for some reason. Right.
Right. Like Leslie Kelbling likes to talk about background utility, right? Somehow there's some notion of yes, if you just tell the robot I want the dish in the I want the sink clear, let's say, then like somehow there's something implicit about don't break the dishes, don't throw a dish at grandma or whatever, like, I don't know, but there's something else that you have to write down if you really don't want crazy things to happen. But I don't know if multi-objective is the right way. I think there's probably bigger architecture questions about layered control. My thinking is taking me more towards sort of how do you compose multiple controllers into a full architecture, and maybe the architecture would protect you. You would have lower level controllers that would never throw something out of the sink, and then maybe you specialize. So, not to say that I'm against a multi-objective formulation. That's just not where my head has been.
Sure. No, it's fair. Okay. Maybe one last question, because before we let people go. In Europe, it's getting super late. The question is, it's from Jia Fang. I see that the dense descriptors that Russ talked about is also trained from a neural network that captures the correspondence, and probably people would do control RL on top of those representations. How do you compare such approaches to just run neural networks end to end? What are the benefits?
Yeah. So, okay, most of the people who talk about pixels to torques kind of control, most of them have a big perception network first that goes into a smaller control policy network, and they tend to pre-train. Even if you're going to do end-to-end training in the end, that the perception need is on this big network that tends to be needed to be pre-trained, whether it's from ImageNet or whatever. So for us, it's in that space, and instead of training end-to-end, one of the things that's really good about the dense descriptors is that they can be trained on your robot, on your data, self-supervised. So basically, the robot can just wave its camera around or move some objects around in front of it, and it comes up with this rich perceptual representation with very little human effort. And it gives us that pre-trained perception network, which we then hand to whatever controller we want, whether it's a robot whisperer one, whether it's an optimization-based, model-based optimization one, or whether it's an end-to-end trained deep one. So I feel that it's more interpretable than arbitrary latent representations that could come out of a perception network trained out of an autoencoder or whatever. There's other reasons why we kind of like it, but certainly the self-supervision is pretty convenient.
Okay, good. So there is a Discord server. I don't know whether you're interested in joining. I'm happy to share the link to you. So that's where all the participants are hanging out. And I'm pretty sure that there are some people who would be interested in, you know, like poking a little bit more. There are also like maybe we can refine the problem descriptions to arrive at something tangible, and that could also happen there. So I said, like, it would be really great if you were open to just being on the server for a while.
I'm happy.
Okay, all right.
I'll check my email for that.
Yeah, I send you an email. I see that you say that like you're not checking your emails, so, but I'm going to send you an email. It's like
I can look for specific emails. I have the capability.
Just that single email. I promise it's going to be short. Okay, it was great having you, and thanks for everyone attending the bootcamp, watching online. And hope you had a great week, and looking forward to the whole semester and further interactions with everyone who was involved. Thank you.
Thank you for organizing it. It was a great week.
Yeah, our pleasure.